皆さん、Scawthornでございます。私の発表について、初めての考えことは、私の発表が、日本語とか英語、どちら発表しましょう。I finally decided to speak in English so as not to subject my Japanese friends and colleagues to a painful experience listening to my poor Japanese. This year marks the 50th year since I came to Kyoto University. And it has been a 50-year exploration of how I might be able to contribute in a small way to reducing death and destruction in the world. I'd like to share with you my journey in doing that, and I hope you find it of some interest. You will see that not only is it a recitation of 50 years of my life, but also in many ways a history of risk management or modern risk management today. So rather than give a talk on one technical subject, although I will in the second half of the talk speak largely about a technical subject I've done some work in, I believe it might be of more interest to you on how I came to Kyoto University and where it took me. The journey began in Brooklyn, New York, where I was born, and under the shadow of the Brooklyn Bridge, which is approaching 150 years old and one of the great engineering structures, one of the first large suspension spans in the world, and a great engineering structure. And I went to high school very close to that bridge at Brooklyn Technical High School, which is a special school for studying engineering. And I studied structural engineering there. I then, as was mentioned, I then received a Bachelor of Engineering degree from the Cooper Union in Manhattan, a small school most people don't know about, but which is highly esteemed in some circles. And I then received a Master of Science from Lehigh University in Pennsylvania, which prided itself on having the world's largest testing machine at that time, a 5 million pound universal testing machine. And after receiving my master's degree there, I first worked for the electric utility in New York City, Con Edison, which is the equivalent, for example, of Tokyo Electric Power Company in Japan, designing electric transmission towers, as you see here. I actually designed the towers for what was called the PJM, or Pennsylvania, Jersey, Maryland transmission line, which is actually the backbone for electric power in the Northeast United States. And I also worked on various issues having to do with Indian Point Nuclear Power Station, which was owned and operated by Con Edison. Around that time, I also read a book that influenced me greatly, The Death and Life of Great American Cities by a lady named Jane Jacobs. Jane Jacobs was not academically an urban planner. As a matter of fact, I'm not even sure she had an academic degree. But she observed life in New York City and what made the city vibrant and alive and healthy and successful, and what detracted from those wonderful, desirable assets. And she came to write this book. It's a very powerful book. It influenced many people, and it made me interested in why cities are the way they are. I had moved to San Francisco by that point and was working in San Francisco as a structural engineer. And one day I was looking out and I also, by the way, at that time also became interested in the field of urban economics, which is a branch of economics that explains why cities have the shape they are. Having read Jane Jacobs's book, I wanted to know why. And economics is a powerful, it's very much perhaps the strongest determinant of why cities have their shapes. And urban economics, for example, will explain, if you look at a skyline, why building heights or building rents or population densities all decline in a negative, typically a negative exponential curve from the central business district. And this is common from all cities and can be easily shown to be a trade-off between the cost of land, the cost of capital, and the cost of transportation. So one day I was looking at San Francisco skyline, thinking about that, and it occurred to me that the city of San Francisco, which is shown here in this cartoon, with its hills here and its very soft soils near the water, and its concentration of the central business district with its high-rise buildings right on the softest soils in the city, was actually very poorly designed from an earthquake engineering point of view. As earthquake engineers, as structural engineers, we know that the deeper the soils, more typically the stronger the shaking will be in an earthquake, and the greater the damage, everything else being equal. So why had we put the highest concentration of values in the city on the softest soils? In effect, the city was mal-optimized. Instead of being optimized, it was exactly the reverse of the way it should be when you took earthquake engineering or the structural performance in an earthquake into account. And this was a very interesting question for me. I thought to myself, well, what if we just moved the central business district, the CBD, away from the softest soils? Admittedly, it already exists, but if we waved the magic wand and moved it, how far would we have to move it? What would be the delta to reduce the damage significantly? And would that be a valuable thing to do? Obviously, if we moved the central business district hundreds of miles away, we would eliminate the earthquake risk entirely. We would not be near earthquake faults. But then the cost of transportation, the commuting costs, would be absurdly high. And that was not practical. So what is that delta? And I thought to myself, that is a very interesting question. I could do a doctorate on that subject. But where would I do that PhD? Well, it should be a place that has high urban density. And that could be places in Europe or the United States, China, Japan, India. It should be a place with a long record of high seismicity, because I was going to look at the influence of earthquakes on urban form. And it should be a place, if I was going to spend 4 or 5 years studying, it should have an interesting, rich culture. And I thought, well, that would not be in the United States. Not because the US doesn't have a culture that in some ways is interesting and rich and vibrant. But if I was going to be returning for education, I wanted to learn a foreign language and experience a foreign culture. So when I put all these things together, only one place jumped out at me. That was Japan. I should come here to study this subject. And I did. That's me with the mustache. I'm the one with the mustache, by the way, in this photograph, with Professor Yoshikazu Yamada, Professor Hirokazu Iemura, and many of my other colleagues in Yamada Ken back in 1976. And I spent 4 years in Yamada Ken pursuing this question. Eventually in 1981, writing a dissertation on urban seismic risk, its mitigation and analysis. I was hoping also to have it be mitigation, analysis, and policy. But after 4 years, I realized I was not perhaps a policy person, more a technical analyst. And I attempted to provide an integrated study of the seismic risk of an urban region and analyze the constituent elements and how we might reduce that risk. I used Osaka as a case study, developed my own form of geographic information system before such things existed, and plotted the damage in this very crude manner at that time, the concentration of values and where they might be and how it might move and so on. And I took the equations from urban economics and introduced a new term, the damage term, which in effect is a damage function. So this simple tent-like structure would be the urban form without taking into account earthquake risk. And when you took earthquake risk, the central business district, the highest buildings, would move over to here, and the form would change in this manner, given this damage function. Where here we had high damage, so the CBD moved away, and here we had little damage, and the CBD tended to move towards that. And actually, I found that depending upon the subsurface conditions, you only had to shift the CBD a few 100 meters to have enormous savings in the capital requirements, since you didn't have to build so strongly for earthquake, and in the expected future damage, present value of the expected damage that would occur in an earthquake. I published these, a number of chapters came out of my dissertation that were published in journals on the vulnerability of buildings in Japan due to shaking. I looked at 3 agents of damage: shaking, liquefaction, and fire following earthquake. 3 of the major. I did not look at tsunami, but shaking, liquefaction, and fire following earthquake are certainly major agents of damage in Japan. I published in the economics journal this theory, and I published a paper, the first probabilistic model on fire following earthquake for urban post-earthquake fire hazard. I also then, when I returned after receiving my doctorate from Kyoto University, I returned to San Francisco, and with National Science Foundation funding, did a similar study for the city of San Francisco, coming up again with similar results. You only had to move the CBD a few 100 meters to realize really enormous savings. Now, we're not going to move the CBDs, but this could be a guide for future zoning so that over the decades, the central business district is shifted. Whether that will ever happen, I doubt it, frankly, but it was an interesting theoretical study, and it satisfied my curiosity. But in the course of that, I learned many things. I learned how to model fire following earthquake and shaking. I learned, in general, probabilistic risk methods. And following that, my career has been recited. I worked as a consulting engineer for about the next 20 years, then returned to Kyoto University, where I was only professor for 5 years, reaching the mandatory retirement age, then was a visiting professor at these institutions, and have engaged in consulting with 1 foot in academia doing research and 1 foot in consulting. And it's a symbiotic process where the research feeds the practice of engineering, and the engineering practice feeds the questions to research. Worked on many kinds of structures. This is the Arecibo Radio Observatory that no longer exists but was in Puerto Rico, and in James Bond movies. And I did a seismic analysis of that as a structural engineer, and published a number of books and papers on these topics. I also, at that time, was very interested in, again, trying to reduce death and destruction. And one of the greatest sources of death and destruction in the world are low-strength masonry buildings. They exist throughout, as Professor Alcantara Ayala has mentioned, in the Global South. These are unreinforced masonry buildings. take various forms of adobe, bajareke, or other kinds of construction. And I did again, under the National Science Foundation funding, I performed the first shaking table test of a full-size adobe building at University of California at Berkeley, and joined a committee and contributed to the development of the International Association of Earthquakes Engineering's guidelines for not improving the earthquake performance of non-engineered construction. This is India, Iran, Latin America, much of Asia has construction of this type. And these guidelines have been used and improved over the last several decades to reduce the construction quite a bit. The other members of the committee were all very distinguished: Professor Arya from India, Teddy Bowen from Indonesia, and so on. I was very fortunate to work with them. But the fundamental thing that I had learned at Kyoto University was this method of probabilistic risk analysis. And as we all know, by now this is common knowledge, risk is really the intersection of hazard, vulnerability, and the assets or values at risk. When you take these things, you need some sort of a risk engine to integrate these factors to measure your risk. But each of these factors, such as hazard, is again the intersection of earth sciences, typically, of seismology, geology, and other fields. The vulnerability is, again, the intersection of materials science, structural engineering, and the dynamics of structures and so on. And there are other fields I'm not mentioning here. And the values, again, are the intersection of the economics and other values that are associated with assets. So we must combine all of these. So risk analysis is a multidisciplinary integration of all these factors. But at that time, in the early 1980s, it was really not being very well applied. For example, insurance, which is basically the business of managing risk in California in 1980, did not use probabilistic methods at all. Earthquake insurance in California was very cheap, very underpriced. The risk was actually much more expensive than what they were charging for it. There was people more and more, because of the 1971 San Fernando earthquake and other earthquakes, the demand was rising. And a very interesting process had occurred, where back in the 1920s and back in the 1800s, in the 1920s and 30s, the insurance industry actually had much better knowledge of its risk than it did by the 1980s. Back in the 1800s, they had mapped every building in cities. The Sanborn Company, for example, was one of the leaders in this field, mapping the risk. And an underwriter, any insurance underwriter, could look up any building, see exactly how many stories it was, what the occupancy was, whether it contained any vulnerable fire materials or other hazardous materials, whether it was a brick or wood or some other construction, where the exits were. They could see all of this in a book that every underwriter's office had. But by the 1960s, this was regarded as old-fashioned, and all of this technology was eliminated. And underwriting was based simply on, if we haven't had a loss in the past, it must be a low risk, so we'll charge very little for it. And of course, this omits the fact that some risks are infrequent, such as earthquake or other natural hazards. They only occur once every few decades or even centuries. So this statistical approach failed. But the insurance industry didn't realize this. In fact, they knew almost nothing about the homes and buildings they insured. When I started to try to apply probabilistic risk methods for the insurance industry, the very first, they were interested when I explained to them what economies could be achieved with more accurate understanding of their risk. They said, great. And when we started trying to do this for them, the first question we had is, well, where are your risks? And they gave us a list of their risks with the addresses. But many of the risks had the same address. Hundreds of the risks, hundreds of the buildings would have the same address. And it turned out that was the mailing address. That's where they thought their risks were, where they sent the bill. They had no knowledge whatever of what they were insuring. Then in 1984, a small earthquake, moderate-sized earthquake in California called the Coalinga earthquake, further skewed the insurance industry by requiring that all companies have to offer earthquake insurance in California. So some companies withdrew, and this created a crisis. And there was an asymmetry of information. The primary insurance companies were at the risk of the reinsurers, such as particularly Swiss Re and Munich Re, who had started to use probabilistic risk analysis and would use the more accurate information that they had to get a better deal when they offered reinsurance to the primary insurance companies, the so-called asymmetry of information. All of this led to what became known as the birth of the modelers, the model companies. And there were three of them that were all born about 1982 or 83. And those were a company called RMS, originally called Risk Management Solutions, started by Professor Haresh Shah at Stanford University. A company called AIR worldwide. AIR stood for Applied Insurance Research, started by a lady named Karen Clark actually in Minnesota to begin with. She was working for a brokerage there. And a company called EquiCat, which stood for Earthquake Engineering Catastrophes. They were born due to the convergence of the probabilistic risk methods, which came out of pioneering work here in Japan by Professor Kawasumi, and in the United States by Professor Alan Cornell, and in Mexico by Professor Luis Esteva and Emilio Rosenbluth. And also that the probabilistic risk methods had recently been started to apply to the nuclear power industry. So in a way, it was a trickle down from the nuclear power industry in some ways. It also occurred because by the early 1980s, the personal computer had emerged, and it provided computational power to these companies that they didn't have before. So these three companies were born, again, Karen Clark, EQE, I was basically a founder of it, and RMS, Risk Management Solutions. There was little industry by the insurance industry at first, but the interest increased after several cat losses. The first couple, the Whittier Narrows earthquake, the Lone Prieta earthquake, really didn't capture their attention. But then in the United States, the 1992 Hurricane Andrew and the 1994 Northridge earthquake very much captured their attention, and they started to understand the benefits that probabilistic risk analysis would bring to their business. Now, what is probabilistic risk analysis? Well, we start with a collection of assets, for example, these buildings. This is termed a portfolio. And threatening this portfolio is some source of hazard. It might be an earthquake fault. It might be a typhoon or a hurricane, or it might be a flood. Whichever one of these hazards occurs, its effects vary depending upon location. But that is the source, the fault, and so on. And that source has a frequency severity curve. In earthquake engineering, it's called the Gutenberg-Richter magnitude frequency relationship. And it's typically a semi-logarithmic relationship. And in the other fields, it has other names. They're all basically a manifestation of a more general statistical law called Zipf's law. And they all basically follow the same pattern. And as I said, the actual intensity of the earthquake shaking or the wind speeds or the flood depth will vary depending upon the distance of the asset and the topography and other factors from the source. So this would be, in earthquake engineering, this would be the ground motion model. So that attenuates with distance. And that has a relationship also. You can see here, the site intensity goes down, the hazard. Now, every structure, every asset has its vulnerability. That is the relationship between its, between its, the hazard and the degree of damage that it will sustain. So when you integrate over these three curves, using what looks like a very complicated equation, but actually is simply simple accounting of these in a probabilistic manner, you actually get the frequency of losses as a function of these various factors here, the probability, the intensity, the damage, and so on. This is the fundamental risk equation. It's written in, different people write it in different ways, but it basically consists of these elements. And what you get out of this is the probability or the frequency of loss. Larger losses have very small probability or frequency of occurrence. They occur perhaps only once in a few hundred years. And more frequent losses are much smaller, such as shown here. And the area under this curve, if you integrate it, is what's called in the insurance industry the pure premium. That is the actual amount of expected loss that the insurance company expects to pay. And the actual premium that they charge you or me is the pure premium plus their overhead costs for paying for their salesmen and clerks and so on, and their profit. And that's basically how the insurance industry today operates. And if you wanted to include, for example, I've been talking about natural hazards here, but and climate change, of course, has emerged as a factor that affects natural hazards. You just the climate change, all it does is increase the frequency over here, the frequency of the event severity, and eventually will change the curve here. So we integrate climate change into this equation very easily. Now, by 1994, again, we were starting to make some headway with the insurance industry in educating them. And we had the Northridge earthquake, which occurred at about 10 minutes to 5 in the morning in Los Angeles. And by noon, we had generated this map of, it's a very simple map, admittedly, but it was a computer-generated map using our models of the shaking intensities that were expected from that event. We got from the USGS, we got the epicentral intensity, the epicentral location and magnitude. And with that, we could generate the shaking intensity map. And by early in the afternoon, within about 8 hours after the earthquake, we had estimated all the damage that would occur in the Los Angeles or Southern California region. And this was the first intensity map and losses generated in real time for any earthquake in the world. And it was the governor of California. First, we had a telephone conference call with the governor of California, explaining to him what we had done and how we estimated the losses to be on the order of $30 billion. And he thanked us very much, ended the call, picked up the call and called the President of the United States, explained to him the data that they had used, and that was used to create the presidential declaration. It was the first presidential disaster declaration based on a computer model. And that was then used, and so on. And we estimated not only the total damage, but the amount of insured losses that would accrue to the insurance industry. Now, I won't go into it, but in actuality, these losses were underestimates. They were made the same day of the event, and we underestimated the total loss. There are many reasons why we underestimated those, most of it having to do with poor data. But the insurance industry still did not know much about what they were insuring, and we were using the best data we had at the time. But the next year, and I was here when the Hanshin-Awaji earthquake happened. And as a matter of fact, this is me with Professor Takeda from Kobe University, as a leader in lifelines at the time. And this event led to the rise of risk management, the application of risk management in Japan. the Japanese insurance companies were lagging a few years behind the US insurance companies in understanding that this new technology was emerging. But with this earthquake, they quickly understood the value of it. And it also led to a broad increase in structural retrofits in Japan, of course, and the Japanese insurers adopting the probabilistic risk modeling. And as a matter of fact, I often joke that I came for an academic meeting. I was here for a US-Japan meeting. I'd flown in the night before and the earthquake happened. I'd come for 5 days and I wound up staying for 2 years because I opened the Tokyo office of our company at that time and we started serving the Japanese insurers. It then became apparent that this technology should not only be applied to insurance companies, but it should be more broadly applied for the benefit of everybody. And the Federal Emergency Management Agency in the United States conceived of a piece of software called HAZUS, which stood for Hazards US, a multi-hazards loss estimation methodology using these exact tools. And it was over the next 10 years, it was developed for earthquake, for flood, and for hurricane. And as I made the point, and you can see, basically, the assets, of course, are the same no matter what the hazard is. And the frequency, severity curves are different for the different hazards, and the vulnerability curves are different. But the basic mathematical structure are exactly the same for all these hazards and for others. And in fact, for all hazards, they can all be modeled basically the same way. So HAZUS was developed. I had the privilege of leading the development of the flood model for the United States in this methodology here. And HAZUS has gone on to be used for many years now to model and manage earthquake, flood, and wind losses in the United States. And comparable programs have been developed in many other countries. Mexico, for example, developed a comparable series of software programs. I developed basically the same models for Morocco under World Bank funding, and many other countries have done this. I don't think Japan has, I'm not sure, but I don't think Japan has a national model for, it has, of course, national hazard models, but I don't think it has national loss models. I think they're still used, loss models are primarily used by, developed by private companies, but I'm not sure about that. This is a very complicated graph. I apologize for this. What you see, what you see in the, this is time from about 1950. And this is development of the analysis methodology I'm talking about. Starting about 1950 up to 2000, these light blue bars are data from Munich Reinsurance Company showing the increase in natural hazards with time. And these are adjusted for inflation. So why are they increasing? Well, the fundamental factors, the fundamental reasons they're increasing are in absolute amounts is population growth. I think the world's population virtually doubled during this period. And also increasing concentrations, urbanization. Many countries in 1950 were primarily rural populations, where by 2000 they were primarily urban populations. So when you get concentrations like that, you lack the benefit of what's called dispersion, and your cat losses, your catastrophic losses or cat losses can actually be much higher. And that's what's happening. Now, I know you can't read most of these, but these are different events. And I've described some of them, such as the equations developed by the hazard analysis methodology developed by Cornell, Esteva, and others. And those are what some of these things are here. And later, perhaps you might want to strain your neck and try to read what these are. But these were all different contributions, primarily by academics, that increased our knowledge, that led to, by first, on our ability to better understand assets, which again, there was this gap here where the insurance industry lost its knowledge of assets and then had to regain it. The hazard analysis improved, and vulnerability studies began about 1970. on how structures are affected by natural hazards. And by convolving all of these, we could, and then there was the rise of the personal computing power. And so this led to risk analysis methods and the development of different modeling companies and the hazards and other risk analysis software. So that's kind of the history of risk analysis. And this led to, once we had these probabilistic risk models were fully integrated into the insurance industry, they started to innovate with these and create things such as cat bonds, and I'll explain what those are. It became apparent that once we had these tools, you could take an area around Tokyo, for example, and divide it into, you could, first of all, do the calculations that I've already described using those equations I presented and estimate the probabilistic loss. But from a cat point of view, another way to look at it would, a catastrophe or cat point of view, another way to look at it would be to draw a box around Tokyo and say, if a certain size earthquake happens inside that box, so a very simple measure, do we have a magnitude 7 earthquake inside that box or not? You can calculate the losses then, given wherever that magnitude 7 might be. And based on that, you can actually, and you can take into account deductibles and so on. You can actually calculate a bond, which could be sold to investors, and which would be, in effect, a form of insurance by the people who are selling it. In other words, the transaction was that somebody, for example, in this case, this was a cat bond for Tokyo Gas, that if Tokyo Gas would experience an enormous amount of damage in the event of a large earthquake near Tokyo, but Tokyo Gas could then issue a bond, with the transaction being that if you buy the bond, I will pay you coupons on that bond over 20, 30, whatever the life of the bond is. But if an earthquake of a certain magnitude occurs within a certain box, then I keep all the money you paid me for that bond and you get no more payments. So in effect, it's allowing people, by buying a small bond, to, when you add all those bonds up, to offer insurance of a very large amount to a large company like Tokyo Gas. So this was the emergence of what was called the cat bonds, or cat in a box, as they came to be known. These were parametric triggers. Parametric meaning that it was simply a magnitude within a certain parameter, a magnitude within a certain geographic area. And these came to have significant benefits for large assets in many countries, in Japan including, when compared with traditional insurance. Now, why were they better than traditional insurance? Well, cat bonds could be sold, they're bonds. They can be sold on the capital markets. That means Wall Street, rather than in the insurance markets. And at that time, around 2000, the total amount of capital available in the world to all insurance companies was on the order of $400 billion. It's a lot of money. But the amount of capital that was available on Wall Street and in the Kapitocho in Tokyo and in the London financial markets and so on was about 20 times that, on the order of, well, actually more than that even, $5 to $10 trillion in value. So that meant you could access a greater supply of capital, and therefore, since there's a greater supply, the costs are lower. And this is a way, this transformed the insurance industry. And this led to what were called alternative risk transfer tools. And one of them that I was involved in, for example, was a swap, what became known as a risk swap between Tokyo Gas and İGDAŞ. İGDAŞ is the Istanbul Gas Company. And Istanbul, of course, has had earthquakes in the past and is actually still expecting, just like the Tokai Jishin here in Japan, they are expecting a large earthquake near Istanbul, which will happen someday. And of course, we are expecting large earthquakes in Tokyo. And Istanbul in 1999 had sustained 17,000, Turkey has sustained 17,000 deaths in the Izmir earthquake. And of course, in Japan, 6,000 deaths in Kobe. So we know that we're still vulnerable to these things. So the idea was create a cat bond, but instead of selling it on the markets, just sell it to Igdash, and vice versa, Igdash sell it to Tokyo Gas. And they would swap their risks. In effect, they would pool their risks. So this was another kind of alternative risk transfer methodology that has now become very popular in the financial world. So about this time, then, I came to Kyoto University, and Professor Kenzo Toki had retired, and there was a search, and I was fortunate and honored to be selected to lead his former laboratory, working with, at that time, Associate Professor Junji Kiyono and Assistant Professor Yosuke Ono, who I should correct that now. Professor Kiyono has retired. The laboratory is now headed by Professor Aiko Furikawa, and Ono Sensei is now Professor and Vice Dean at Tottori University. I was honored to work with them. Now this was the Jishin Bosai Kenkushitsu. It was a laboratory primarily concerned with earthquakes and infrastructure. So I became interested in the issues of infrastructure, such as a water system here. This is just one example. Again, just like most hazards have, when you step back and look at them, they have the same mathematical form. Most lifelines also have the same mathematical or topological arrangement, which is that you have sources. Let me go back a sec. You have sources, such as a reservoir. You have transmission. You have some terminal reservoirs of some sort. This is for water. And then you have a distribution system. So in effect, you have the heart, the arteries, and then the capillaries, if you analogize to the human body. And this is true for electric power, water, and many other types of lifelines. Now, many earthquakes have shown that our urban lifelines are vulnerable to earthquakes and other natural hazards. And over time, many cities, and I'm using here the American cities as an example, Seattle, Portland, San Francisco, Los Angeles, had all reinforced their dams and their major transmission lines, so they could get the water from the source to the last mile with some reliability. But they still had not tackled the problem of making their distribution system more earthquake resistant. Why? Well, because actually it's a much more difficult job than fixing the transmission lines. The transmission lines in most cases are one or two, admittedly large pipes that run hundreds of miles or kilometers, but they are, in terms of rebuilding them or strengthening them, they are manageable. In large cities, we're talking about thousands of kilometers of 10, 20, 30 centimeter diameter pipes, which cannot all be replaced at once. And as a matter of fact, from a financial point of view, cannot be replaced in any reasonable amount of time. It's just too expensive. It's too much. So the question emerges how to deal with this problem. And there's two fundamental approaches. One is to, excuse me, keep hitting the wrong button here. One is to create selected lines and reinforce selected lines. So you create what's called a resilient grid. And this is being implemented in Los Angeles, for example. And the other is to go through and use probabilistic risk methods to try to analyze which pipes are the most important pipes in the network. Most important from the point of view of which ones probabilistically contribute the most loss, which is a combination, it's the intersection of the pipe vulnerability and the transmission capacity of that pipe relative to the distribution network. time does not permit me here to go into solving the most important pipe problem, but I have papers on this. We developed something called the pipe algorithm for prioritizing the problem to solve that problem. But fires have always been a problem in the United States and in Japan. We know that from, if nothing else, 1906 and 1923, when the two largest urban conflagrations in history occurred due to earthquakes. And this is a montage of San Francisco, modern San Francisco, and the same place in 1906, showing the people watching the fire then and so on. And fires remain a huge problem today, as we saw in the Kobe earthquake in 1995, and as we saw just a year ago in January in Los Angeles, where we lost about 15,000 homes in a matter of hours. This is the Eaton fire in January 2025, an aerial photograph. That's all on fire. So they remain a problem today. And this can be analyzed analytically. This is, for example, work I did for the U.S. Geological Survey showing the fires that would break out after a magnitude 8 earthquake on the San Andreas Fault in Southern California. And we have here about 1,600 fires that will occur within the first 24 hours, given that earthquake. And this dwarfs the capacity of the fire departments to put these fires out. So we have the same problem we had in 1923. We still have it today. And using the methods I described earlier, you can calculate the distribution of the probabilistic distribution of losses that you may sustain. And the mean estimate here is about 160,000 single-family equivalent dwellings or houses that would be lost. Now, of course, not all of these are houses, but we use that as the basic measure to communicate that. And compounding this problem is that the water systems are going to be damaged. This is 1906. This is 1989 in Long Prairie earthquake. This is the Kobe earthquake. The pipes are going to break. So the firefighters, even when they get to the fires, will not have water. So the fundamental problem is how to assure water for firefighters at the site of the fires following an earthquake. And that's what I wanted to describe next. These are the water systems. First, we'll just look at it in a very simple way. These are the water systems for Seattle, Portland, Oregon, Los Angeles, and San Francisco. The red represents areas of very weak soils, such as I described earlier, where the central business district is on, for example, right here. And these are old swamps that were filled in. And we can, just to start off slow, we can model that system as a very simple system of water network where each of these gray lines is a city block fed by a small distribution pipe, typically on the order of 15 or 20 centimeters in diameter. And every 5 or 10 blocks, there will be a larger line, what's so-called trunk line, that helps, sort of like an expressway, that helps to maintain the pressure across the system. And the entire city is fed by transmission lines that come in here to terminal reservoirs and then go up and feed another couple of terminal reservoirs at these locations. So basically all the water is coming in along those two red lines to a reservoir here, which goes out along the trunk lines and then goes out through the light gray lines to your house. So and if we analyze the system under ordinary non-earthquake conditions, we can see that we have do a hydraulic analysis. We have adequate pressures virtually everywhere. But if we then subject the city, idealized city, to an earthquake, what we see here is up here, the blue dots represent pipe breaks for a modified Mercalli intensity of 6. This is about, on the Japanese JMA scale, MMI 6 is about roughly JMA 5, probably, or high 4. And we can see we had some pipe breaks, and the red represent fires, a few fires that are going to break out. And we can see the pressure distribution. And this is also a depiction of the pressure distribution. And this area here is going to have no water. But it's not so bad. There's going to be 29 leaks and breaks and the fires and so on. And we're going to need about 70,000 gallons per minute, or about 280,000 liters per minute of water for the city. But this is manageable, even though there's some breaks. But if we subject it to stronger shaking, such as MMI 8, which is about JMA 6, we see that we get, of course, we get many more breaks, many more fires, and the entire system loses pressure. So this is the recipe for a conflagration, just as it happened in 1906 and 1923. So, and this, by the way, is actually for San Francisco is threatened right here is the San Andreas Fault, which in 1906 ruptured with about a 7.8 magnitude, and is capable of magnitude 8, and is only 3 kilometers from the fault to this location here, 3 kilometers. These are breaks in the distribution system. So again, we look at an idealized system or we look at a real system, we're going to have so many breaks that the system is going to lose all of its water, which is what happened in 1906. And it's ironic that San Francisco is surrounded on 3 sides by the Pacific Ocean, the largest body of water on Earth, and yet it burned down for lack of water because they couldn't move the water from here to where the fires were. And this is an old story of 1906, but it's a story last year in those Eden fire, in the Los Angeles fires. The hydrants ran completely dry. The system could not meet the firefighting water requirements of the firefighters. And actually, in a way, it's not feasible to do that. And the fire risk is huge. This is San Francisco, and to quote a former fire chief, the city is built to burn, just like much of Japanese cities are too, with wooden buildings. It's all wood construction, and it's built to burn. So we are looking at a huge future conflagration here. Now, this was recognized back in 1906. As a matter of fact, it was recognized in 1905 by the fire chief. And he proposed in 1905 to build a special water system separate from the drinking water system, build it to earthquake-resistant standards, and it would be used to fight the fires. But it was rejected. In November of 1905, it was rejected by the Board of Supervisors of the city, and 6 months later, the earthquake happened and the city burned down. So, just like locking the barn when the horse leaves, in 1908, they built the high-pressure system that the fire chief had proposed. He had unfortunately died in the earthquake, but they built the system. And you can see it here. This is the pipe network. It's 200 kilometers of special earthquake-resistant high-pressure pipe from 1908 design with 2 pump stations. This is pump station number 1. The way the system is designed, it has 3 pressure zones. It has a reservoir at the highest point in the city, which is 40,000 tons of water. And then it has a 3 million liter tank here just to step the pressure down, and another 3 million liter tank here, again, to step the pressure down. And then the system, again, feeds this part of the city. And this has been maintained and improved since 1908 and still functions today. It's called the high-pressure system. Additionally, because the losses were so huge, they also built cisterns or underground tanks. This is one under construction in the 1980s. And there were over 200 cisterns around the city, underground water tanks in San Francisco. No other American city has anything like this. This is the firefighters. When they're finished constructing it, all you see is a manhole. You take the cover off of that, and the tank is below ground, and the fire engines can pull the water, draft the water out of the cisterns. No other American city has anything like this. Tokyo has 14,000 cisterns. Japanese understand this problem very well from 1923. But even Tokyo or Osaka do not have high pressure system like that. Now, this is a system built in 1908. You'll notice, and that it was primarily, you'll notice it's very dense in this area here, which is because that was where the city existed at the time. At that time, this was all country. There was nothing out here, sand dunes. But by today, all of this, matter of fact, by the 1950s, all of this had been totally built out. And there's buildings everywhere here, and they don't have a high pressure system, and we know the low pressure system is going to fail. So as a result, San Francisco now is designing a new separate potable emergency firefighting water system called POOFs, being built in this area here. And I'm involved in the design of that. It is a dual purpose system. Under ordinary conditions, it will be a series of trunk lines providing more water transmission capacity up to this part of the city. But in the event of an earthquake, it will, seismically actuated valves will shut the system and isolate it from the drinking water system, and it will become a high pressure system just like the other system here. High pressure, by the way, we're talking 3 megapascals of pressure. It's quite high. It's a billion, just building this is $1 billion project that began 10 years ago and is going to take about 20 years in total to complete. But the question is, okay, that looks nice, but how big should it be? What do we design it for? And how big should the POOFs be? What should be its capacity? And now I want to walk you through the process by which we're working on that. The analysis methodology starts, of course, with the earthquake and the pattern of ground shaking that we expect. That pattern of ground shaking, combined with the building density and the materials of construction, allows us to estimate where the ignitions will be in the city. And for each of these ignitions, we need to get water out of a fire hydrant. So we therefore lead to a pattern of water demands on the system. These are probabilistic. Then we can supply that water from one of 3 sources. The potable drinking water system, but we know that's going to fail, as I showed you. The high pressure system, which is what we're designing, and the cisterns. The cisterns are a backup to this system. So really, we're designing this system to meet these demands. However, these will all be affected by ground shaking and permanent ground deformations, which we know will create a certain amount of damage from various relationships, which will damage the system and degrade it. So we'll still be able to provide some of these supplies, but not all of them. And we wind up with a system reliability curve here, which then feeds back because some of these fires then will not have water and they will grow larger, which again then increases the demand, goes back through this curve here. We need more water. We come back here, the fire is larger. We go back, we need more water, and so on. So it's kind of a vicious cycle. To model this, we use Monte Carlo methodology, in which we run this process thousands of times to calculate the distribution of ignitions and water demands that we need to design for. And the result is a probabilistic distribution of the fires in the burnt area and the water required. I should mention, by the way, the ground motions are not simple. They're spatially correlated, and we take into account spatial correlations in the ground motions. Why? Because it's a double whammy, where the spatial correlation means that under a particular situation, the high intensity ground motions will cluster in a certain part of the city. And that cluster not only creates more fires, but it degrades the fire system above average. It degrades the water system above average, which means you have less water than you would think on average. And those two together, you have the above average number of ignitions, and the loss of the water pressure, so you get a double whammy leading to a conflagration. So we take that into account. So it's vital to consider spatial correlation. We also take into account the topography and the liquefaction susceptibility shown here. And you can see the permanent ground displacements that have occurred at various locations. not only do we look at the main shock, but we look at the aftershocks. And just going through, the aftershocks are governed by two basic laws, Bota's law and Omori's law. I think some of you are familiar with these. And without going into a lot of detail, we take that into account because there will be at least one or two aftershocks on the day of the earthquake. To calculate the ignitions, we look at the assets at risk, the building data. This is the density of low-rise buildings, the density of high-rise buildings. There are many trees in San Francisco, so that's another form of fuel. We know we have wildland fires. We're going to have tree-fed fires in San Francisco, so we take that into account. We look at the materials of construction. Red here is wood construction. So you can see, again, that photograph I showed you, San Francisco is largely built to burn. And we look at the age of construction of the different buildings. You can see here the city went through several periods of high construction and then low construction, such as World War I, the Depression, and so on. By this point, the city had already been built out, so there's very little new construction. We surveyed all the buildings, and because there's different kinds of fire vulnerability, or different kinds of construction in California, so we take those into account, whether it's platform, so-called platform or balloon type of construction. And we look at which buildings are sprinkled. We have data on all the buildings that have sprinklers, and many of those sprinklers depend upon the low pressure system for pressure, and they will fail. But some of them, especially in high-rise buildings, have a backup water system, a tank, and we take that into account. We take into account the spacing between every building and the future growth. We're not building for today. We're building the system to meet the city as it continues to grow. We estimate the city will grow by 50% by the year 2050. It has a population now about 800,000, and we expect it will be 1.2 million people in 30 years. And so we take that growth into account. We also look at what's going to change over the future. San Francisco is phasing out as part of trying to be greener and improve the situation with regard to climate change. San Francisco is phasing out gas. Gas is used in California for cooking, just like in Japan, for cooking, for heating homes, and for heating hot water. But since 2021, San Francisco has mandated that all new buildings must be all electric. They're phasing gas out. And this is happening across that. But when you phase out gas as a source of energy, you must replace it with another source of energy. And that is, San Francisco is now mandating that all new buildings must install solar panels. So this is another source of fire. We're getting rid of the gas, which reduces our fire risk, but we're introducing solar panels and battery electric storage systems, and they are a new source of fire. And what the trade-off is here, whether the fires are going to be less or more because of this, we tried to analyze, we don't really know, but that's another question. Lastly, San Francisco has a system you don't have in Japan of what are called trolley buses, which are electrically driven buses driven off of overhead wires. This wire network in some places can be very dense, and we expect in an earthquake that some of those are going to fail and come down and prevent passage of the fire engines to get to the fires. So we've mapped all that out and take that into account. So doing all this, conflating all these different factors, we come up with an average or mean probability of ignition across the city. And this is the start for us designing that water system. We have to do all of this in order to this is the demand, and the water system has to have the capacity to meet this demand. So this is the demand. The average number of ignitions is shown here for this magnitude 8 earthquake. And on average, we expect about 50th percentile is 50th percentile, 174 ignitions on average in the city in the first 24 hours after the earthquake. Now, to put that in perspective, on most days, San Francisco will have 1 or 2 fires. On a bad day, it'll have 4 or 5. We're talking about 170 fires here. Clearly, we've got a problem. That's why the city is spending billions of dollars on this. A key vulnerability, by the way, is the hydrant system. The hydrants, where the fire department can connect to the water system to get firefighting water, are different in the United States than they are in Japan. In Japan, you have below ground hydrants. It's just a yellow box on the street. The firefighters open that up and connect to it to get their water. In America, we have above ground hydrants shown here. We have the water main. We have what's called a lateral that comes off and goes up, and the firefighters connect here. But this is, especially here, this is a key source of vulnerability. In 1989, I documented the breaks that occurred at this elbow, and there's typically a crack that occurs across this elbow. So we are now doing finite element analysis and trying to design a new type of elbow that will not have that same vulnerability. This is, again, the finite element model of the whole system here that we're doing. So getting to the end here, all of this can be modeled. And what we wind up modeling here, there's 1,000 simulations. Each one of these lines is a simulation. We have 1,500 minutes, so the first 25 hours. And this is the amount of water that is required for the whole city of San Francisco to fight fires. And in some cases, it's enormous amounts of water. It's 1.5 million gallons per minute of water. That's 6 million liters per minute of water. It's enormous amounts. But on average, in other cases, it's not so much. So you can see here, the heavy black line is the median demand, which is also shown. And this, by the way, to put this in perspective, this level here is the total Tokyo Fire Department's entire pumping capacity. If every fire engine in Tokyo Fire Department, which is 20 times the size of San Francisco, were pumping, this is how much water they would use. And this shows at the 25th hour, the distribution of flow per minute that would be required. And this would be Tokyo Fire Department's capacity. So using these curves, we can calculate the size of pipe and the size of pump stations that are going to be required throughout the system. And this is all, on this basis, the city will be spending $1 billion. So, however, given this though, you need to decide what's my design point. And right now, the city the design point eventually becomes how much money do I have and what does it buy me? So the design point in this case, we're using a working hypothesis of having 75% reliability. In other words, meeting 75% or 3 out of 4 fire demands under all possible cases. And we estimate that that probably is good enough. And that's going to cost about $1 billion. If we wanted to provide a higher reliability, for example, 90%, we're talking about $5 or $10 billion, which the city can't afford to spend. Even $1 billion is a lot of money. So, and this final design point will be decided. It hasn't been decided yet, but right now the working hypothesis is 75% reliability. So I could go on, but I will stop at this point. I just have a couple more points to make. These are some of the disasters I've surveyed over the years, earthquakes and hurricanes, typhoons and floods and other things. And I could just talk about those for quite a bit, but I won't. But I do want to talk about, lastly, GADRI. Professor Alcantara Ayala gave a very nice talk about GADRI, and mine's not quite as detailed, but I do want to discuss it for a moment. When I was retiring from Kyoto University, I had a discussion. I thought to myself, disaster research institutes exist around the world. I can name dozens of them, and there are many more I can't even name. And yet they don't talk to each other very much. And I started thinking about that, and I thought to myself, the oldest, arguably the oldest, and certainly the largest disaster research institute in the world is here in Uji. And it would be completely natural for Bosai-ken, DPRI, to provide leadership to all the other disaster research institutes in the world through some sort of a global alliance. And I had the discussion with Professor Tatano, and he thought that was a good idea, and mostly, almost entirely, he took that idea, and over the last 18 years has, as Professor Alcantara Ayala described, grown GADRI with the help of a few other people, with the help of many people, has grown GADRI into what it is today. And I'm very pleased and gratified to see GADRI become what it has been today. And I hope it continues to prosper and provide leadership for disaster reduction around the world, and through GADRI, BOSAI Ken. So I want to thank BOSAI Ken and the people of Japan for sponsoring GADRI over these years and helping making it a reality. And I want to thank Professor Tatano and Wilma James and Ayuna Matthews particularly, and many other people that have helped to make GADRI what it is. So in summary, Kyoto University allowed me to pursue a question: how to manage urban seismic risk. I have pursued that question for 50 years in the myriad facets that are a city. A city has just all these different dimensions: building damage, financial risk, infrastructural performance, human casualties. I haven't spoken about crowd dynamics and so on, fire spread and so on. Time has allowed me to only go into a few of those facets today. I am deeply honored to receive the DPRI award, especially when I join the other DPRI fellows, starting with Professor Kanamori, a giant in seismology, and going through all the other recipients, including Professor Collins, most recently, number 11, Professor Alcantara Ayala, Professor Bard, Jim Goltz, and others. I'm deeply honored to be included in that company. Because of Kyoto University and DPRI and many other people in Japan, I've been able to do some of the things I described, and perhaps those have been a small contribution in some way to natural hazards risk reduction. And certainly that was my goal. I dedicated my career to that. I've learned much in Japan, not only science and technology, but also courtesy, generosity, harmony with nature, and many other things, some of which are ineffable, that cannot be described, but all of which I have gained from, and which I am deeply appreciative to Japan and all of its people for. I have so many people to thank, beginning perhaps with Professor Yamada, Toki, Amano, Iemura. Many of these names are known to you: Kameda, Kobayashi, Sato Sensei, Kiyono, Ono, Tatano, and so on. Particularly Professor Yamada and Professor Iemura. Iemura was the assistant professor when I joined Yamada Ken. He later became the professor there. And Iemura-san is still with us, but he's not able to be with us today. And on the right is his wife and my wife and myself. Iemura-san is one of the finest men I've ever known. He's a wonderful, kind man. I thank him and Professor Yamada, but I thank, as again, everyone I've mentioned and everyone in Japan. So, domo arigato gozaimasu.